Hi students, this is continued part of previous lesson where I am discussed about isomerism coordination compounds. Basically two types of isomerism, that is structural isomerism, stereoisomerism. In the previous lesson I am discussed about structural isomerism, different types of structural isomerism. Now in this session I am going to discuss about stereoisomerism. Stereoisomerism. So what is stereoisomerism? So the compounds which are having same ligands attached to the same central metal atom, but the arrangement of ligands around the central atom is different. That means the spatial arrangement of ligands around the central atom is different. So those two compounds are called stereoisomers, and the phenomenon is known as stereoisomerism. Okay, I repeat it again. The compounds which are having same ligands attached to the same central atom, but the arrangement of ligands around the central atom is different. So those two compounds are called stereoisomers, and the phenomenon is known as stereoisomerism. So basically stereoisomerism is two types, that is geometrical isomerism and the second one is optical isomerism. Okay, so geometrical isomerism and optical isomerism. So first geometrical isomerism. So the compounds which are having same ligands attached to the same central atom, but the arrangement of ligands around the central atom is different, either in cis position or trans position. That means cis trans isomers. So cis isomer, same side, trans isomer opposite. That means same ligands, same number of ligands are arranged adjacent to each other. Arranged adjacent to each other. That is cis isomer. So same ligands. Same type of ligands arranged on opposite side. That is trans isomer. Okay. Next, optical isomerism. So optical isomerism, the solutions of when a plane polar light passes to the solution of complex compounds, that solution of complex compound rotate their plane polar light towards left or towards right. That is, if it is anti-clockwise direction, that is left, that is levo rotatory. If it is clockwise direction, that is right, that is dextro. Okay, that is D and L isomers. Okay, so first I am discussing about geometrical isomerism and then optical isomerism. First, let's discuss about geometrical isomerism. So geometrical isomerism. So first, geometrical isomerism in 4 coordinated complex. Geometrical isomerism in 4 coordinated complexes. In 4 coordinated complexes. Right. So 4 coordinate complexes. That we are having two types of 4 coordinate complexes. That is tetrahedral, square planar. Tetrahedral, square planar. So geometrical isomerism cannot shown by tetrahedral complexes. Tetrahedral complexes. First one, tetrahedral complexes. So cannot shown by, so geometrical isomerism cannot shown by tetrahedral complexes. Why? Because so here, so this is the structure of tetrahedral complexes here. Okay, so the bond angle between two ligands, that is 109 degrees 28 minutes. Here all the ligands are adjacent to each other. That means only one isomer, that is cis isomer, because so this ligand is adjacent to this isomer, this ligand, and this ligand is adjacent to this ligand, and this ligand is adjacent to this ligand. Okay, so all these ligands are adjacent to each other. So that means there is no possibility for spatial arrangement, different spatial arrangement. That's why tetrahedral complexes does not exhibit any geometrical isomers. Okay. And the second type, that is square planar complexes. So square planar complexes. So square planar complexes shows geometrical isomerism. And let's see how they show. Right. So square planar complex of the type MA4. Square planar complex of the type MA4. That means the 4 ligands are same. So the complex square planar complex of the type MA4 and A3B, that means 3 ligands are same and 1 ligand is different. So these two the square planar complex of these two type of square planar complexes are not shown by this geometrical isomerism. So geometrical isomerism cannot shown by this type of square planar complexes. Why? So this is the square planar complex, right? So this is yellow ball is central atom, and the 4 ligands in along x-axis, along y-axis in a planar. Yes, that is square planar, right? If the 4 ligands are same, that means all ligands are same. If you interchange these 2 ligands, you get same structure. If you interchange these 2 ligands, here you also are getting same ligand. If one ligand is different, even the one ligand is different, so this ligand is because of these three ligands are same, if you place this ligand in this place, you get same structure. Okay, if you put all these 4 places, that different ligand, you are getting same complex, same structure. So you are not getting any geometrical isomers for these 2 type of square planar complexes. And next, geometrical isomerism shows in the square planar complex of the type MA to B2. The 2 ligands are different. That means, for example, I will show you. So here, right? So, okay. I will put another ball. Right. So here this square planar complex, these 2 ligands are same, these 2 ligands are same. Now here this complex exists in 2 types, that is cis isomer and trans isomer. Cis isomer. So cis isomer, that is M A B B. Okay. So this is cis. Here 2 ligands. Here 2 ligands are in same side. 2 ligands are same, so that is cis. That is the complex is like this. Right. So this is the complex. The 2 ligands are same. So 2 same ligands on adjacent positions. So this complex is a cis isomer, right? Same side. Next, trans isomer, that is M A B B. Right. So here same ligands, same type of ligands arranged on opposite side. Okay. So that is trans isomer. Okay, cis isomer and trans isomer. Right. So this is trans isomer. So same type of ligands are arranged at opposite direction. That is trans isomer. Okay. So here 2 types. So this complex will exhibit 2 geometrical isomers. Right. So one is cis, another one is trans. Okay. Next, M A B C D. That means 4 ligands are different. 4 ligands are different. If the 4 ligands are different, that means all these 4 ligands are different. Let's take an example. Right. So here 4 ligands are different. Okay. So how many geometrical isomers exhibited by this complex, this square planar complex? If the 4 ligands are same, let us fix one ligand. Okay. If you fix one ligand, now changing these 3 ligands. The first ligand, first isomer, that the black ball, which is placed trans to this ligand. Okay, this is one isomer. Next, red ball, which is placed trans to this ligand, second isomer. Next, white ball, which is trans to this ligand. So that is third isomer. That means here 3 isomers are possible, right? That means here you are getting 3 geometrical isomers. So example of this complex, right? So let us discuss examples. So example of this complex is PTNH3 twice Cl2. Okay, so this complex exists in a cis isomer and trans isomer, that is platinum NH3 Cl. So this is cis complex, cis isomer, and platinum Cl NH3. Okay, this is trans isomer. Okay, cis isomer and trans isomer. And the next, if we discuss platinum NH3, the example for MAB, 4 ligands are different. NH3 H2O Cl Br. Okay, so 4 ligands are different. So this complex shows 3 geometrical isomers. This complex shows 2 geometrical isomers. Okay, if 3 ligands are different. Okay, if 3 ligands are different. Sorry, 4 ligands are here. 4 ligands are different. They shows 3 geometrical isomers. Okay, if next the ligands are bidental ligands. Let's see example for that complex. Complex of the type MAA twice. AA means bidental ligands. MAA twice. Okay, for example, so nickel ethylene diamine twice. Example. So ethylene diamine AA, here 2 donor atoms are same. Ethylene diamine NH2 CH2 CH2 NH2. So NH2 CH2 CH2 NH2. Here 2 donor atoms are same. So that's why here represented AA, bidentate ligand. So how many here coordination number is 4, not 2, because here ethylene diamine is bidentate ligand. That's why 2 into 2, that is 4. Here 4 ligands are 4 donor atoms are same. One ethylene diamine here 2 nitrogens. Another ethylene diamine you are having 2 nitrogens. That means nickel nitrogen CH2 CH2 NH2 NH2. Here also NH2 CH2 CH2 NH2. Okay, this is a square planar complex. NH2 CH2 CH2 NH2. So NH2 CH2 CH2 is the 4 donor sites, that is nitrogen. So all the 4 donor sites are same. So that's why this complex does not showing any geometrical isomerism, because all the 4 donor atoms are same. So that's why this complex does not showing any geometrical isomer. If you change these 2 ligands, if you interchange these 2 ligands, you are getting same structure. That's why this complex not showing any geometrical isomers. Okay, let's take another example. AB twice. So AB twice means AB also bidental ligand, but the 2 donor sites are different. Let's say an example, glycine. Okay, so that means nickel bis-glycinato. Okay, bis-glycinato nickel 2. Okay, right. So glycine, structure of glycine, first let's say structure of glycine, that is NH2 CH2 C double bond O minus, and having here one donor site is nitrogen and second donor site is oxygen. So one donor site nitrogen and second donor site is oxygen. Here both the donor sites are different. That's why I am writing AB. It is a bidental ligand because it is having 2 donor sites. One is nitrogen, one is oxygen, right? Let's say structure of this complex, that is nickel NH2 CH2 C double bond O NH2 CH2 C double bond O. Okay, here so here 2 nitrogen and oxygen, here nitrogen and oxygen. So if you interchange these 2 ligands, so this isomer is 2 donor sites, nitrogen, same ligands, same donor sites on same side. Here also nitrogen, here also nitrogen. So that's why this isomer is a cis isomer. Okay, so this complex exhibit geometrical isomer, because if you interchange these 2 ligands, if you interchange these 2, if this is called chelating ligand. So this type bidental ligands forms a chelating type ring type structures. That's why those are called chelated complexes, chelated ligands, right? So the second isomer is nickel O C double bond O CH2 NH2, nitrogen CH2 C double bond O oxygen NH2, right? So second square planar complex. So here nitrogen in opposite side. That means this isomer is a trans isomer. Okay. So the square planar complex of the type MAA twice. the two donor atoms are same in bidentate ligands. So those complexes are not showing any geometrical isomers, but the complex of the type of square planar complexes are M, AB twice. Here two donor atoms are different, like glycine H2, CH2, C double bond O minus. Oxygen donates one lone pair and nitrogen donates another lone pair. So this complex, this ligand is a bidentate ligand. So example, if you see the structure of these two, so if you interchange these two ligands, here we are getting another isomer, that is trans isomer, cis isomer and trans isomer. Okay. So this is geometrical isomer is 4 coordinated complexes. Okay. I hope you got it. And the next geometrical isomerism in 6 coordinated complexes. Geometrical isomerism in 6 coordinated complexes. So 6 coordinate complexes means octahedral complexes. Octahedral complexes. So octahedral complexes of the type M, A6. If all 6 ligands are same, if all 6 ligands are same, that means if you take an example, so this is the octahedral. So structure of octahedron. Here along x-axis 2 ligands, along y-axis 2 ligands, along z-axis 2 ligands. So we are having octahedron. Octa means 8, hedron means faces. So 8 faces we are having. 8 trigonal faces, 1, 2, 3, 4. In the same way, 1, 2, 3, 4. So total 8 faces we are having, right? So 8 faces, that's why it is a octahedral complex. Now of the first type of MA6, MA6 complex of the type MA6. If all 6 ligands are same, if you interchange these two ligands, you are getting same structure. If you interchange these two ligands, you are getting same structure. Okay. So one more thing I want to tell you here, the positions, right? So here first 1, 2, 3, 4, 5, 6. Okay. 1, 2, 3, 4, 5, 6. Here 1, 2 are 6 positions adjacent. Okay. 90 degrees. 6 position and 1, 3. 1, 2, 3, 4, 5. So 1, 2. So these two ligands are in cis position. So these two ligands are cis position. Here 1, 3 also cis position and 1, 4 also cis position. 1, 5 cis position. So 1, 2, 1, 3, 1, 4, 1, 5 cis position and 1, 6. 1, 6. So these two ligands are opposite. So this is trans isomer. If two, okay. So this is. Here having 1, 6 is trans. Let's see another. For example, this is 1. Okay, 1. So here with respect to this ligand, so these 4 ligands are cis to each other. Okay. So with respect to this ligand, all these 4 ligands. This is square plane. Now if you taking this ligand, so this is a planar square planar plane. So the ligands with respect to this ligand 1, 2, 1, 3, 1, 4, 1, 5. So all these 4 ligands are cis position to this ligand, right? Now this ligand is trans to this ligand. Okay. If you take this ligand, okay, this ligand, all these 4 ligands are cis. That means 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6 is trans. Okay. These are the positions of cis and trans positions in octahedral complexes. Okay. Right. So if you complex MA6, all 6 ligands are same. If you interchange any 2 ligands, they are getting same structure. There is no spatial arrangement of ligands. That means they are not showing any geometrical isomers. Next, MA5B. MA5B. If you change one ligand, if you for example, so I am having different ligand. Okay. So this is different ligand. On 5 ligands are same, one ligand is different. So if you place this ligand in this position, you are getting one structure. Okay. Now change this position. Okay. If you change this position, interchange these two ligands. Here also you are getting same structure. Okay, identical structure. So there is no spatial arrangement because all these 4 ligands are same. 1, 2, 3, 4. Okay, all these 4 ligands are same. So and here also same. So here cis position ligand and trans position ligands are same. Okay, so that's why with respect to this ligand, these 4 ligands are cis position, this ligand is trans. If you change these two ligands, you are getting same ligand, same complex. If you change these two, you are getting same. So there is no spatial arrangement of ligands. That's why MA5B not showing any geometrical isomer, right? Next, complexes of the type M AA thrice. So this complex is also not showing any geometrical isomers because here AA, I told you na. So AA means bidentate ligands. Bidentate ligand having same donor sites. Bidentate ligand having same donor site. So same donor sites. That's why all the donor sites are same. All the donor sites are same. That means here one bidentate ligand. For example, if you take ethylene diamine NH2 CH2 CH2 NH2, you are having two donor sites. That is at the either end. That is nitrogen. You are having 3, that means 3 into 2, that is 6 nitrogens. So 6 nitrogens are same. If you change any 2 nitrogens, you are getting same structure. There is no spatial arrangement in the complex. That's why you are not getting any geometrical isomers for this complex, right? Right. Next, so these complexes are not showing any geometrical isomers. Next, M. So example for this complex, CONH3 6 times 3 plus CONH3 CO NH3 6 times 3 plus. So this complex not showing any geometrical because all the 6 ligands are same. All the 6 ligands are same. So if you change any ligand, you are getting same structure, identical structure, no spatial arrangement in the complex. And here CO NH3 5 times Cl 2 plus. So this complex also not showing any. So example for this complex. Okay, example for this complex CO. So 5 ligands are same, 1 ligand is different. Here also not getting any geometrical isomers, right? And MA CO En thrice. So all these 3 ligands. So all these 3 ligands are same. That means all these bidentate ligands, ethylene diamine bidentate ligand. So all the 3 bidentate ligands are same. That means all the donor sites are same. So that's why this complex also not showing any geometrical isomers, right? Next, complexes of the type complex of the type MA4B2. Let's take an example. MA4B2. Let's take an example. That is CONH3 4 times Cl2 plus. I am taking an example. See, the 4 ligands are NH3. Sorry. So 4 ligands are same, 2 ligands are same. Total 6. Coordination number is 6. Now this complex shows a geometrical isomer because if you see the structure of this complex, so this is the structure of complex, right? So this is the structure of complex. Here 2 ligands are arranged in either side, that means opposite positions. Okay, 1 comma 6 position, 1 comma, so 1 2 3 4 5 6. So these 2 green bars are chlorines. These 2 green bars are chlorines. These 4 white bars are ammonias, and yellow ball is cobalt. Okay, so if you place these 2 chlorine atoms in opposite side, that is 1 comma 6 position, so this isomer is trans isomers. Okay, so one complex exists in a trans isomer. So if you interchange these 2 ligands, here you are getting cis isomer because 1 comma 2 position are cis isomer. So these 2 ligands are adjacent to each other. In the previous case, 1 comma 6 positions are trans positions on opposite side, but here these 2 positions are cis. Okay, so these 2 are cis. So this is cis isomer, and here previously I am showing that is trans isomer. That means this complex shows 2 geometrical isomers. 2 geometrical isomers. So if you draw the structure, Cl, Cl, NH3, 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 NH3. Okay. So this is so 2 chlorines on same side. So this is the structure. Okay. Structure of this complex. So 2 chlorines on same side, adjacent to each other. So this isomer is a cis isomer. And the next one is a CO, chlorine, chlorine, NH3, 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 NH3. Okay. So this is a trans. So here 2 chlorines on opposite side, two chlorines on opposite side. So this is trans isomer. So this complex exhibit two geometrical isomers. One is cis and second one is trans. Okay. Next, octahedral complexes of the type Ma3B3. Three ligands are same. Ma3B3 complexes, octahedral complex of the type Ma3B3. Three ligands are same. Okay, let's take an example. CO NH3 thrice Cl3. So this is an example of this type of complex Ma3B3. So you have three ammonia ligands and three chlorines. Okay. Next, the first isomer is if you place these three chlorines, green balls are chlorine, white balls are, let's say green balls are chlorine, white balls are ammonia, and yellow ball is cobalt. Okay, right. So first 1, 2, 3, 4, 5, 6. Right. So 1, 3, 2, 1, 2, 3. So 1, 2, 3. So this is with respect to these two ligands, these cis positions, these two are cis positions, and these two are also cis positions. Okay. So all these three ligands are cis positions to each other. So this isomer is cis isomer, and also these three ligands are on one face. That means this is facial isomer. Okay, facial isomer. If you see the structure, NH3 Cl 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 NH3 NH3 NH3. Okay, so these three chlorines on one face. So this is a facial or cis. So facial isomer. This is facial isomer, and the second isomer is if you interchange these two ligands, right? These two ligands or these two ligands or these two ligands, right? So these two ligands, if you interchange these two ligands, you are getting another isomer. Okay, so that is these two ligands are in trans position, right? Trans isomer, right? Here. So these two ligands are trans positions to each other, opposite positions, same ligands on either side, that is in opposite side, that is trans isomer. So this isomer is trans isomer, and so this is 1, 2, 3. So this meridional. So this is known as a meridional. So this is meridional isomer. CO Cl 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 NH3 NH3 NH3. Okay. So 1, 2, 3. So these two chlorines are opposite side. These two chlorines are opposite. So this is trans on meridional. A trans. So meridional, trans. Okay. So this complex, octahedral complex of this type exhibit two types of geometrical isomer. One is facial, and second one is meridional. One is cis and trans, right? And next, so complexes of the type M A8 twice A2. That means two bidentate ligands and two monodentate ligands. Here coordination number is 6, not 4. Here because here it is a bidentate ligand. Here having two same donor sites. So here two donor sites, 2 into 2, 4, and here monodentate ligands plus 2. So 4 plus 2, that is 6. Coordination number is 6. Octahedral complex. Let's take an example. CO N twice Cl2 plus. So number of geometrical isomers exhibited by this complex. Let's see. Okay, complex CO, right, NH2, CH2, CH2, NH2. Okay, so NH2, CH2, CH2, NH2, and NH2, CH2, CH2, NH2, chlorine, chlorine. Now, so what type of isomer it is? Either cis isomer or trans isomer. Yes, it is trans isomer, right? Trans isomer, because two chlorine atoms are same side. Two chlorine atoms are opposite side, opposite to each other. So this is one ring and this is second ring. Here four ligands are same. So you can't say either cis or trans with respect to these four nitrogens, because all these on square planar plane, all these four nitrogens are same. So we can say cis and trans with respect to chlorine, right? So these two chlorines are on opposite side, 1,6 position. So this isomer is trans. Okay. Next, if you replace these two, if you interchange these two ligands, if you interchange these two, here you are getting another isomer, that is Cl, Cl, NH2, CH2, NH2, CH2, and NH2, CH2, CH2, NH2. Okay, this is one ring, this is another. Here two rings on opposite side. Okay, two rings on opposite side. Here two rings in adjacent side. Here two chlorines on opposite side. Here two chlorines on adjacent side. So this is a cis isomer. So this is cis and this is a trans. Okay, because two chlorines on adjacent side, adjacent positions. Okay, so this is geometrical isomerism in a 6 coordinate complex. If you take another example like M AB thrice, that means here three bidental ligands, but those bidental ligands having different donor sites. What is the example? I told you na, glycine. So here example CO glycine thrice. So glycine, what are the glycine? You are having one negative charge. Here cobalt is +3 oxygen state. Okay. CO so glycine, what is structure of glycine? NH2, CH2, C double bond O minus. Okay, this is glycine. Nitrogen, one donor side, oxygen, another donor side, right? So nitrogen and oxygen. Okay, NH2, CH2, C double bond O. Nitrogen, NH2, CH2, CH2, and O. Okay, I am taking for simplification, I am taking the structure like this. Okay, now here this is a cis isomer or trans isomer. Just observe the structure. Here nitrogen, okay, nitrogen, this is plane. So above the plane here having one nitrogen, on the plane here having two nitrogens. That means these three positions are cis positions. So this isomer is a cis isomer. Okay, nitrogen and these two nitrogens are cis, these two nitrogens are also cis, and these two oxygens are also cis, and this position, and these two oxygens are also cis position. So this complex is a cis isomer. If you see the trans isomer, just interchange these two ligands. That is N O N N okay. So this is the complex. Here NH2 CH2 C double bond O. Okay. Here nitrogens on opposite side. Here two nitrogens on opposite side. Here two oxygens are opposite side. So this is a trans isomer. So this is cis isomer and this is a trans isomer. Okay. Okay. Next example. So octahedral of the type M A2 B2 C2. So octahedral complex of the type Ma2 B2 C2. So let's take an example. CO NH3 twice H2O twice Cl2 complex CO NH3 twice H2O twice and Cl2. So this complex will show five geometrical isomers. So this we can try. You just arrange these 6 ligands in 5 ways. Okay, that's why you are getting 5 geometrical isomers. So around the central atom, so all these 6 ligands, arranged in 5 different ways. Okay, 5 different geometrical isomers here you are getting, right? Next complex of the type M A B C. If all ligands are different, A B C D E F. Okay, A B C, all 6 ligands are different. Okay, here 3 ligands are same. It means 2 ligands are same. Here all 6 ligands are different. Let's take example. Okay, CO NH3 H2O CO Cl Br F. Okay, so this is 1 2 3 4 5 6. So 6 ligands are different. Okay, 6 ligands are different. So these 6 ligands are arranged around this central atom cobalt in 15 different ways. Yes, that means here we are getting 15 geometrical isomers. Okay, so this complex all 6 ligands are different. So all these 6 ligands are arranged around the central atom in 15 different ways. Okay, so that means 15 spatial arrangements around the central atom. So here we are getting 15 geometrical isomers. Okay, so these are this is all about geometrical isomerism. And the next type that is optical isomerism. Okay, second type of stereoisomerism, that is optical isomerism. Optical isomerism. So optical isomerism. So what is optical isomerism? So when a plane polarized light, so when plane polarized light passes into the solution of complex, so that complex compound, if that complex compound rotate this plane polarized light towards right, that is clockwise direction, clockwise or anti-clockwise. So either clockwise, that complex solution, that complex compound, if the complex compound rotate this plane polarized towards left or towards right, so that complex compound is optically active and shows optical isomerism, and the phenomenon is known as optical isomerism. Okay. So here two types of isomers here are getting. So if the complex rotate plane polarity towards clockwise, that is right side, that is we are getting D isomer. Okay, right. If anti-clockwise, if the plane complex compound rotate plane polarity towards left, so that is LEVO isomer we are getting. Okay. That is, if the plane complex solution complex compound that rotate plane project towards the right side, that clockwise direction, then we are getting the isomer. If the complex compound rotate plane project towards left side, that we are getting LIVO, that is anticlockwise, that is left hand side, that is we are getting LIVO isomer, right? The conditions to show optical isomerism. Conditions to show optical isomerism. So what are the conditions? So conditions to show optical isomerism, that means the compound should be, the first condition, there are two conditions. The first condition should be compound should be complex, should be asymmetric or achiral. Compound should be asymmetric or achiral. So should be asymmetric. So asymmetric means they are not having any symmetries. The complex compound should not contain any type of symmetries like plane of symmetry. For example, if you see the complex, so this complex here having three planes, that means you have one, okay, so one, so along this plane 1, 2, so 1, 2 and 3 planes, okay, 1, 2, 3 and 4, 5 between the atoms, between the ligands, along the ligands and between the bisecting ligands, right? So these are the planes. So the complex should not contain any type of plane of symmetries and not contain any center of inversion. You know how many types of symmetries? Mainly three types of symmetries. One is the plane of symmetry, center of symmetry, axis of symmetry. So complex compound should not contain any type of this type of any kind of symmetries like plane of symmetry and the center of symmetry and axis of symmetry. Right? Compound should be asymmetric. Right? And that is the first condition. And the second condition is complex and its mirror image. The object and its mirror image. Complex and its mirror image should be non-superimposed. So non-superimposable to each other. So mirror images are non-superimposed mirror images. So these two are the conditions to show geometrical isomers. Particle complex, if particle complex to show geometrical isomerism, that complex should not have any type of symmetries like plane of symmetry, center of symmetry and rotational axis of symmetries. And second thing is the mirror images of the compound are non-superimposed. That means let's say this mirror image of this hand is left hand and right hand. So if you place a mirror between these two hands, you are getting these two are mirror image to each other. And if you imposed this hand on this left hand side, these two are non-superimposed and this is superimposed, right? So this is superimposed and this is the non-superimposed. Okay, so mirror image should be non-superimposed, right? So these two are the conditions, right? So let's see different examples to show in optical isomerism. Right. First, optical isomerism, four coordinate complexes. Four coordinate complexes. So four coordinate complexes. So four coordinate complexes we are having two types, that is tetrahedral and square planar. So tetrahedral complexes. If you see the complex, the shape of tetrahedron here, if the ligands are different, if all ligands are same, we are having plane of symmetry. Okay, so this is plane. If you pass plane between these two and central atom, these two ligands and central atom, these two are also same. That means we are having plane of symmetry. Okay, so this complex should be if the tetrahedral complex are having same ligands, so that would be optically inactive and not showing any optical isomer. But tetrahedral complexes having different ligands. If all the four ligands are different, if any two ligands are same, that shows that not showing any optical isomer because they are having plane of symmetry. to exhibit optical isomerism, the tetrahedral complex must having 4 different ligands around the central atom. The 4 ligands are different. They shows optical isomerism MABCD shows geometrical isomerism, and MA4, MA2, B2, MA3, B all are not showing. All these type of tetrahedral complexes are not showing any optical isomerism. So complex tetrahedral complex of the type MABCD shows a geometrical isomer, because this complex not having any type of isomerism, and mirror images are non superimposable also. Okay, next square plane complexes. So square plane complexes not showing any optical isomerism. Because square plane complex is planar, so you are having plane of symmetry. You are having plane of symmetry. So if you see the example, so here example, right? So right. So if you take an example, this one, so this is square planar complex, right? So here you are having plane of symmetry. All 4 ligands are present in one plane. So this is plane of symmetry. So all 4 ligands are same. All 4 ligands are same. So that's why square plane complex are not showing any geometrical isomerism. Okay, sorry, optical isomerism, right? So in geometrical isomerism, tetrahedral complex are not showing any geometrical isomerism, but optical isomerism shown by tetrahedral complexes of the type all the 4 ligands are different. Next, the square plane complexes geometrical isomerism shown by square plane complexes of the type MA2, B2 and MAB twice. Okay, but optical isomerism is not shown by this square planar complex, because here having plane of symmetry. Okay, 2 conditions you have to fulfill to exhibit optical isomerism. One is not having any type of symmetries like plane of symmetry, center of symmetry and axis of symmetry, and mirror images are superimposed to each other. Okay, so mirror images are non superimposed. Okay, and next optical isomerism in 6 coordinated complexes. Okay, clear? So optical isomerism 4 coordinate complexes. So 4 coordinate complexes are having 2 tetrahedral square planar. So optical isomerism shown by tetrahedral complexes of the type all having 4 different ligands. Okay, and next square plane complexes. Square plane complex not showing any optical isomerism, because we are having plane of symmetry, right? Next optical isomerism 6 coordinate complexes. So if you take first type MA6, octahedral complexes of the type MA6. So all 6 ligands are same. All 6 ligands are same. So let's take example CONH3 6 times. CONH3 6 times. All the cobalt we are having 6 ligands, that is 6 ammonia molecules. Let's say white balls are ammonia and blue ball central atom, that is cobalt, right? Okay, now this complex is it complex showing any optical isomerism? No, because it having a plane of symmetry, center of symmetry, axis. It is having all types of symmetries. So first condition is not fulfilled. So that's why this complex is not showing any optical isomerism, and not showing geometrical isomerism also. So this complex not showing geometrical isomerism and optical isomerism, right? So because we are having a plane of symmetry here. If you consider this plane, okay, plane like this. Okay, so if you consider this plane, so these 2 atoms are same, both having mirror image to each other. Okay, so that's why this complex having all this type of planar symmetry, and also having center of symmetry also. At the center, if you taking the point, so 2 atoms are at same distance, right? And rotation axis of symmetry also. If you rotate 90 degrees, you are getting same structure. If you rotate 180 degrees, you are getting same structure, right? Next, now showing optical isomerism. Next, MA5B. MA5B also not showing any optical isomerism, right? This is so complex of the type MA5B. CONH3 5 times Cl2 plus. So here this is chlorine. All these 5 white balls are ammonia. This yellow ball is cobalt, right? Now this having is this complex showing optical isomerism? No, because it's having a plane of symmetry. Now if you pass plane along this square planar plane, okay, if you pass plane along this central atom and 4 ligands, so these 2 atoms, these 2 ligands are same, okay, reflect to each other. mirror image to each other. So this complex shows planar symmetry, shows planar not having any chiral center. Okay, right. So that's why. So this is achiral, asymmetric. That's why this complex also not showing any optical isomerism and not showing any geometrical isomerism also, because if you interchange these two ligands, you are getting same structure. No spatial arrangements around the central atom. Okay, right. Next, MA4 B2. MA4 B2 shows geometrical isomerism. One is cis, another one is trans. So these two B. For example, CONH3 4 times Cl2, if two chlorines are placed in 1, 2, 1, 3, 1, 4, 1, 5 positions, that is cis. If you place these two chlorines in 1, 6 positions, you can get a trans isomer. But this, for example, cis and trans, taking two isomers, let's check whether it is having any symmetry or not. Right. So here, if you consider this plane, or if you consider this plane, if you consider any plane, here you are getting a plane of symmetry. So this complex having planar symmetry, and cis isomers also having a planar symmetry. Trans isomer having planar symmetry, and cis isomer also having planar symmetry. If you passing this plane, so here, if you passing a plane along this two chlorines and two ammonias and one cobalt, passing these two, and these two are same. So these two are mirror image to each other. So this complex having a planar symmetry, now showing optical isomerism. Next, MA3 B3, CONH3. So examples of all these complexes I am given in a geometrical isomerism. Okay, you can see there. Next, so three complexes, three ligands having same. So geometrical isomerism is exhibited by this complex, two types. One is facial, another one is meridial. I told you na. Right. So what is this? So this is trans, two ligands on opposite side. So this is cis and this is trans. If you are having this type, you consider trans positions, because we are having opposite side. You must consider trans, right? So this is trans or meridional. So this is meridional position. So these three chlorines are meridional position. This is meridional isomer, right? So is this complex shown in optical isomerism? No. So it is also having a plane of symmetry. If you pass a plane along this, okay, right? Okay, if you pass plane along these three chlorides and ammonia, one cobalt, so these two are same. So these two are mirror image to each other. If you reflect these two, this ammonia comes this position, this ammonia goes this position. So you are getting plane of symmetry, right? So this complex also not showing any optical isomerism. Okay, and COAA twice A2. Example of this complex, COEN twice Cl2. Okay, if you see that example for that complex is COEN twice A2. So is this complex shown any geometrical isomerism? Just check yourself. Just think of. Okay, so these are six positions of octahedron, and two positions two chlorides, and this is NH2, CH2, CH2, NH2. So NH2 here black balls are nitrogen, ethylene diamine. Okay, so here NH2, CH2, NH2. The complex shape like this, you can arrange, so you can understand easily. So whether the complex is optically add to or not, you must know the structure of that particular complex. Then only you can identify whether it is optically add to or not, right? So here COA twice NH2, that means CO, example for this CO ethylene diamine, NH twice Cl2. Right? Now here, so NH2, CH2, CH2, NH2. NH2, CH2, CH2, and so two rings. So bidental ligands are forming a chelated ring type structures with the metal atoms. So this is one ring and this is second ring. So barium ligands are forming ring type structures with the metals. That's why these ligands are called chelated ligands. Okay, so one ring and second ring. Two chlorines are above the plane and below the plane. So this is trans isomer. So two chlorines are above the plane, below the plane. So these two chlorines are opposite side. So this is the trans isomer. These two rings are also opposite side. This is trans isomer. So whether this complex is optically active or not, it is optically inactive, not showing any optical isomerism. Okay, so this complex showing geometrical isomerism, two geometrical isomers. This is trans, and this is if you replace these two. If you replace these two, so first this complex having planar symmetry. Okay, here if you pass plane like this, or if you pass plane here, so two atoms having plane mirror image to each other. This plane divides molecule into two parts. Both are having mirror image to each other, that having plane of symmetry. Right now here. Now, if you interchange these two, this is trans isomer. Trans isomer is optically inactive, right? Let's check whether cis isomer is optically active or not. Okay, so this is I drawn structure in a few minutes ago. Just you can see that, right? So this is a cis isomer. Two chlorines are adjacent to each other. Two chlorines are adjacent to each other. This is one ring, this is second ring. CO, En twice Cl2. So cis isomer. So is this complex having optical isomers or not? Just think of. It is not having any planar symmetry. First condition is fulfilled. Just think of. Just check whether it is having any planar symmetry or not. Just see structure, just observe the structure. Yes, it is not having any planar symmetry because this ring in one plane, this ring in another plane, and these two chlorines in cis position to each other. So this complex, this cis isomer are not having any plane of symmetry. So it is having it is optically active. It is optically active. Now the mirror image of this complex is also non-superimposed. So two conditions are fulfilled. So this complex is optically active. Let's see the structure. So CO, Cl, NH2. So here ethylene diamine. So this is one form. So mirror image of this complex. So chlorine, ethylene diamine and ethylene. So here it is D and this is L. Okay, so you are getting two forms. So one is D, another one rotate clockwise direction and anti-clockwise. If it is rotating clockwise direction, that is dextro, that is D isomer. If rotating plane polar left side, that is levo. Okay, so you are getting two optically active, right? And let's take another example. CO. That means M, complex of the type M, AA, thrice. Okay, 3 plus. That means example CO, En, thrice, 3 plus. Here, if you see the structure, CO. So this complex is not having any geometrical isomers because all the donor sites are same. If you interchange any two ligands, you are not getting any spatial arrangement, different spatial arrangement. That's why this complex is not having any geometrical isomers. Now let's see, let's check for optical isomerism. So this complex having any planar symmetry or not? Just think of, just observe this complex. Here these two rings, ethylene diamine. So all these three ethylene diamine rings are in different planes. So this is the xy plane, this is yz plane, this is zx plane. That's why not having any plane of symmetry. So and mirror image of this complex is non-superimposable. So this complex is optically active. So if you see the structure of this complex, CO, ethylene diamine, ethylene diamine, ethylene diamine, CO. Okay, so this is non-superimposed. Mirror image is a non-superimposed. One is deformed, another one is the L isomer. Okay, so this is all about optical isomerism coordination compound.